Well, hello, my fellow Almontians, and welcome back to another broadcast from the bunker. Today, I wanted to go through the lab we did most recently, groundwater movement. Saw a lot of nice results handed in, and some of you guys also had some questions. So let me go through it. Hopefully, we'll make some sense of it for you. Reading your introduction there, talks about fresh water representing only 1% of the total water on Earth's surface. That's pretty amazing. Think about more than 70% of the Earth is covered by water, but only, of course, a small percentage of that is what we can drink. And if it becomes polluted, of course, groundwater pollution, it's pretty easy to do and pretty common, then we have a serious problem. So this lab just addressed how water gets in the ground, the rate at which it does so, how much the ground can hold, things like that. Okay. Make sure you get all your vocabulary completed before it's submitted. This runs through the procedure. We would have had a setup in the classroom where you had 3 different tubes of the different size particles in the soil. Right. The first was the 4 millimeter. There would have been a tube with 4 millimeter beads. The next one, 8 millimeter, and then the next one, of course, 12 millimeter. There would have been separate tubes, and we would have run water through it and timed it and all that other stuff. Okay? There would have been a fourth tube of mixed particle sizes just to see what happens. Remember, if you fill in the spaces between the particles, you decrease the amount of airspace, right? You would decrease the porosity. But in this lab, it was all uniform sizes, so you'll notice on one of the graphs the porosity was the same. All right, well, let's take a look at the first trial here. Oh, but before we jump into that, let me remind you of this from the last lesson. You remember this diagram from the last lesson, I hope? And this is showing you different particle sizes and how it affects the rate of infiltration, right? If you start out filling all of them up with water, without a doubt, the gravel infiltrates the fastest, right? It has the fastest rate. Sand a little slower, silt even slower, and clay almost not at all. And that has to do with the particle sizes there. And this lab, of course, had different particle sizes, and you calculated the rate of infiltration as you did it. Yep, definitely going fast there. Okay, so keep this in mind as we run through the data. Okay. So here we are at our first data chart. I had filled in the size for you, the depth of the soil. That was how far down the water was going to infiltrate. The amount of water required to fill the pore spaces, we would have put a total of 250 milliliters in there. The calculated porosity, right, the pore space is 40%. We recovered 200. So let's fill in the rest of the blanks here, and then we'll do all the blanks on the data charts, and then we'll talk about the graphs. So for rate of permeability, you had to take the depth, 100, and divide it by the time. So 100 divided by 15. Everybody's got your handy calculator. We'll scoot this off to the side here. So there it is, 100 divided by 15. So for your first rate, you should have gotten 6.6. We'll round that to about a 7. Okay. Then it's asking you for water retained. Well, if we put 250 in and we recovered 200, well, how much was still stuck in the tube there? It would have been subtraction. You would have had 50 milliliters stuck in that tube. So that would be a 50 ml down there. Okay. We'll go down to the next data chart here and do a similar task. Same depth of the soil, but this time it took 10 seconds. So 100 divided by 10, obviously 10, but if you want to see it just for comfort, there it is. Your depth of 100 divided by 10 seconds, and you got a 10. So your rate of permeability here was a 10. And now for the water retained, well, this time we put the same amount in, 250, but we only got 220 milliliters back. So if you Subtract those, 250 minus 220, then obviously the soil must be hanging on to 30 milliliters. All right, and we'll scroll down to that last data chart there. This time you have the biggest size particles, 12 millimeters. That's about the size of a marble, just FYI. Same depth of soil, 100, but this time it took even less time, right? No surprise there. The bigger particle, the water can infiltrate faster. So again, you do 100 divided by your 5, and I'm sure you can do that in your head, but we'll do it anyway. 100 divided by 5 seconds, of course, gives you 20 as your rate. And now for water retained, well, take a look. There's 250 again, how much we put in, but this time we got out 240, so it only hung on to the difference of 10. Okay, so that was your data charts. Now let's talk about how to graph this. All right, the first graph is permeability versus particle size. Well, permeability, if you take a look, right here we calculated that. So the first one is 7, the next one was 10, and the last one was 20. So our total range of data, for argument's sake, is 0 to 20, right? So for permeability on the y-axis, you have to go 0 to 20. So in this case, why not skip by 2's? All right, I'll just do a couple of them there so that my marker doesn't get all, well, maybe I'll enlarge it here. All right, so hopefully you got 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. So that's an appropriate interval on the y-axis. On the x-axis, you got to do the particle size. Well, if you remember, the sizes were 4, 8, and 12. So we got to go 0 to 12. And what are we going to skip by that makes sense? Check the number of boxes that you have. Looks like we could skip by 1's. Okay. And 12. Okay, so now to plot this data, again, we're doing the permeabilities. So that's going to be this one, and this one. All right. So the first one for the 4 millimeter, you got a 7. So 4 millimeter up to a 7 is about here. For the second one, the 8 millimeter, we got a 10. So 8 millimeter up to a 10. And for the 12 millimeter, we got a 20. So that goes all the way to the top. Connect your points, circle your points, and that's your first graph. Now for an as statement, remember we always start with the x-axis. So you would say as particle size does this, permeability does that. Well, as particle size increases, permeability also increases. So that's what your as statement's got to be there, right? So as particle size increased, so does permeability. Okay, so something like that for your as statement. All right, and that would take care of the first one there. For the second graph, it looks like it's looking for porosity versus particle size. Well, the particle size, again, is still the same, right? That's still 4, 8, and 12. So you're still going to use the same interval on the x-axis. For porosity, well, take a look at your data. The first one says a porosity of 40. The second one says 40. And the third one says 40. So the porosity is the same. Remember, changing the size of the particles doesn't affect the porosity as long as you don't mix them together. So this is going to be an easy interval here, right? You do by tens. It's this one here, porosity. So let's say you did 10, 20, 30, 40, 50. You wouldn't have to go any higher. And all of them were 40, right? So 4 is 40, 8 is 40, 12 is 40. Didn't matter how big the particle size was, it still was the same porosity. So you would connect it up, circle your points, and your porosity graph looked like that. Now for an as statement, well, what would you say? As particle size increases, porosity stays the same. Okay? So as the size increased, the porosity remained the same. Okay. And now we'll take a look at that third one there. This one is talking about water retained versus the size. Well, once again, it's the same size particles, 4, 8, and 12. So use the same interval. And water retained, let's look at that data. So for the first one, the amount of water retained was 50. Then we have 30, and then we have 10. So the total range would be arguably 0 to 50. So let's skip by fives this time. Okay, and for a 4 millimeter, the water retained was 50. So we'll put that in there. For 4, it was a 50. That's all the way at the top. For an 8, it was a 30. So that's somewhere right here. And for a 12, it was a 10. And that would go right here. Connect up your dots. Circle your points. And for an as statement, well, again, as particle size increases, this time you're hanging on to less water. Okay, you retain water, you're going to swell. You're hanging on to that water. So let's get in there. The as statement. As size increases, the water retained decreases. Okay, a classic inverse relationship there. All right, hopefully that cleared up some of your questions and concerns. As far as the summary questions, I'll run through those quick. How does increasing the particle size affect the following? Well, for pore space, it had no effect, right? For water retained, well, you could refer back to your graph. As the particles got bigger, it retained less water. Time necessary to infiltrate. Well, the bigger the particles were, right, the faster they went in, so it would take less time. And, of course, the rate of infiltration, if you take less time, that means it's a quicker rate, right? Those are opposites. For the second one here, if an area has small particles in the upper soil, that means silt or clay probably, how does it affect the following? Well, runoff, well, you're going to have more flooding, right? If these smaller particles are there, the water can't get in, it's going to flood more. That was a real big issue at the old Yankee Stadium. Every time it rained, they would get a delay of game because the water would just sit in the field and they couldn't play. What they ended up doing, they ended up excavating down several feet, removed all of that. It was a mixture of clay and silt, very heavily packed soils, and they removed that and put a lot of gravel in. And now when it rained, of course, the water infiltrated faster and they got fewer delay of games. Small size particles would give you a more time to infiltrate, which means a slower rate. All right. The third one there, compared to the tube of large particles, what would happen if we mixed them? And we referred to that earlier. If you mix them, you're going to have less pore space because now the little ones fill in the gaps between the big ones and there's less air space in the ground. It'll also make it less permeable, right? Less air space, water can't get in. And it will retain a little bit more water because water likes to cling to things. And if there's a lot more little itsy bitsy spaces to cling to, then the water's going to get stuck in the soil. All right? Capillarity, if you remember, is water climbing up. So remember the Santa Claus analogy. If it's a tighter chimney, Santa can climb up easier. So the smaller particle size would have the greatest capillarity. All right? How far down can water infiltrate? You can answer that a couple different ways. Once you get down to solid bedrock, the water can't infiltrate anymore. Or if the ground is saturated, there's already water in the ground, you can only go so far as where that water is. And the top of that water is called the water table. So it can only get down to either bedrock or until it hits the water table. All right. Number 6, what factors control the amount of water that flows through the soil? Well, those are all these factors up here. The particle sizes, how tightly packed they are, things we've been talking about. All right, and for your summary question there, classic diagram of Long Island. It says, due to the deposition by a glacier, which is how Long Island came to be, how do the infiltration rates differ from the North versus the South Shore? Well, the North Shore has all those big, big rocky beaches, kind of a tough place to, lay out a towel and get comfortable. But because they're such big particles, the water infiltrates very quickly. Whereas on the South Shore, you have more of the silt, the clay, and of course the beach's sand. That finer, those smaller particles takes a longer time for the water to get through. Okay? All right, hope that makes a little bit more sense to you. If you're going over your lab, reviewing it, you want to resubmit, that's fine. If you're handing it in for the first time after I've gone over this, well, you understand you're going to lose quite a bit of credit. You got to have it handed in before the deadline. All right, folks, hope everybody enjoyed the little hailstorm today and nobody got any damage or anything, but I don't think it was that bad. Okay, see you next time.
Ah.